Hey, good afternoon, everyone. You all ready to get going? More L'Hopital's rule? Yeah. Any questions over homework problems or anything? I asked you to maybe look at the first 21 odd from section 3.7. Any issues? Number 15, I'm being asked about. Okay, 15 looks interesting. So we have the limit as x goes to 0. X times 3 raised to the x over 3 raised to the x minus 1. So let's talk real quick about what last class was about. We had L'Hopital's rule, right? Which said that if we're ever taking a limit and we have a ratio where we get 0 over 0 or infinity over infinity, that we can apply L'Hopital's rule, which means whatever this limit is, if that limit exists, it will be equal to the limit of the derivatives of the top and bottom separately. So we just take derivative of the top, take derivative of the bottom. Don't do quotient rule, just take derivatives directly, and then try that limit. And if that has an answer, then that's the answer to the original limit. So in this question, first thing we're going to do is direct substitution. We're going to replace x with 0. I get 0. Let's see what happens here. This goes to 0 times 3 to the 0 is 1. So the top goes to 0 times 1, which is 0. And on the bottom, 3 to the 0 is 1, and then 1 minus 1, that gives me 0 as well. So I have 0 over 0, so I can use L'Hopital's rule. So using L'Hopital's rule, I'm going to put an L and circle it. You can put an H, whatever you want. Just somehow indicate that you're using the rule. And then I take the derivative of the top. So the derivative of the top is a product. I have multiplication between these two things. So I start with first taking the derivative of x, which is 1, times 3 raised to the x, plus, now I need the derivative of 3 to the x. We did that 2 classes ago, I think. The derivative of that would be itself times natural log of 3. I'm using this property. The derivative of a to the x is itself times natural log of a. So I will have 3 to the x times natural log of 3. That's the derivative of 3 to the x. And then finish off the product rule times x. That's all over the derivative of the bottom. And since the bottom has 2 terms, right, separated by subtraction, I can do them individually. The derivative of 3 to the x, well, I just did that. That was 3 to the x times natural log 3. And then minus the derivative of 1, which is 0. So I don't necessarily need that there, but I'm just showing I took the derivative. And yeah, that looks bad, but I don't think it's as bad as it looks. So let me just clean it up. This is 3 to the x, 1 times 3 to the x is 3 to the x, then 3 to the x times natural log 3 times x, and then all over 3 to the x times natural log 3. Now what I'm going to do is just plug 0 in again and see what happens. So if I plug 0 in, 3 to the 0 is 1, plus, let's see, this is 3 to 0, that's 1, times, that's natural log 3, nothing happens there, and then times 0, right? So when I put those together, all of this goes away because 0 is being multiplied through there. So all I have is 1 plus 0 on top. So the top's now headed to 1, which is good. And then on the bottom, 3 to the 0 is 1 times natural log 3. 1 times natural log of 3 is natural log of 3. And so I get 1 over the natural log of 3. That's it. Any other questions? Or did that help? No. Okay. All right, so today we're going to finish up L'Hopital's rule. Next time we'll start chapter 4. We'll get into section 1 of chapter 4. Like I said, this is what we did last time. We were doing L'Hopital's rule. The main thing you have to remember is you can only use L'Hopital's rule if you have 0 over 0 or infinity over infinity. And when I say infinity over infinity, it doesn't matter if you have positive or negative infinity on top or bottom. It doesn't matter. It's just if it's becoming infinite on top and infinite on the bottom, positive or negative, we can use L'Hopital. Now, anything else, we can't use L'Hopital. So we have to be careful. So what we're going to do now is we're going to use L'Hopital's rule to help us find limits when we have some other, different forms where we don't have 0 over 0 or infinity over infinity. We have one of these. Okay, so 0 times infinity, 0 to the 0, 1 to the infinity. I'm going to copy these. I want us to talk about these before we actually do anything. So the whole idea is this. Back when we're taking a limit, right? This is, remember, I'm talking about limits right now. If I take a limit and I get 0 over 0, that's what we call an indeterminate form, which means you can't tell me if the top's headed to 0 and the bottom's headed to 0, you can't tell me what the answer is. You got to do something, all right? It used to be algebra, now we have L'Hopital, right? But 0 over 0 is an indeterminate form. We're not sure what happens. Infinity over infinity, same thing, indeterminate form. Top gets big, bottom gets big. What's that ratio headed to? We don't know. I want to discuss why each of these forms over here in yellow, why are these indeterminate forms? So let's look at the first one. What this is saying is you have a very small number, right? Something that's headed to 0 times a very big, huge number, right? So what happens if I take a really small number and multiply times a really big number? Well, I don't know. It depends on how small that number is, and it depends on how big that number is. Remember, I'm not saying, when I say 0 times infinity, when I say 0, I don't mean the number 0. I mean, it's headed to 0. It's getting smaller and smaller and smaller. Okay, there's a huge distinction because 0 times anything is 0, all right? But 0 times infinity in a limit just means getting really, really small times something getting really, really big. So I don't know what happens, right? That's a question. I have no idea what happens. Look at this other one here in blue. 0 to the 0. What does that mean? You have a very small number being raised to a very small number. So think about this. When you raise something to the 0, right? Like let's say I take the number 4 and I say raise it to the 0 power, not in a limit, just 4 to the 0. That should be 1, because we've learned that anything raised to the 0 is 1. So the way I like to look at it is this. It's like the 0 on top here. The 0 on top is sitting there going, hey, look, I want to turn you into 1, right? Because that's what I do, right? When I raise things to the 0 power, I like to turn everything, the answer, into 1. But the base is sitting there saying, well, wait a minute, I want to become 0. I don't want to become 1. So it's like this tug of war. They're kind of fighting with each other, right? The base is like, I want to be 0. The exponent's like, no, I want to make you 1. And so the question is, who wins? We don't know. We have to do something. There's something we have to analyze further. So that is also an indeterminate form. Is this making sense? No questions? Look at this one, 1 to the infinity. So the base wants to be 1. And anytime you take 1 and raise it to any power, right? What's 1 squared? 1. What's 1 to the 100th power? That's 1. What's 1 to the millionth power? It's 1. So the base is like, hey, I really want to be 1, and then the power doesn't matter anymore. And then the exponents, well, wait a minute, you're not 1. You're close to 1, but you're not 1. And look, if I take a number and I start raising it to a higher power, it's going to want to get bigger, right? If I take 1.1 and raise it to the 10th power, it gets bigger. If I take 1.01 and raise it to the millionth power, it gets bigger. So again, it's this tug of war. The exponent's like, hey, I want to make you big. And the base is like, well, wait, I want to be 1. Please let me just be 1. So they're like fighting with each other and you don't know who wins. Make sense? The last one is still a tug of war, right? The base is like, hey, I want to get real big, right? And the exponents, well, wait a minute, hold on. I'm 0. I like to turn this answer into 1. So the base and the exponent are in conflict with each other. So we don't know what happens. We have to be careful though, because not every single version of this is an indeterminate form. Let me give you an example. What if I had this? What if I had something where my base was headed to, what if my base, so I'm taking a limit, and what if I get infinity on the bottom raised to the infinity? Is that an indeterminate form? Well, the base wants to get big, right? And the exponent's like, well, hey, I'm going to just multiply you times yourself a bunch of times. It's just going to get bigger and bigger and bigger, right? There's not a conflict. They're actually helping each other achieve the goal of becoming infinite. So that's not indeterminate. That's not something we'll have to ever do any work on. Here's another example. What if I have something where I take a limit, the base wants to become 1 and the exponent wants to head to 0? So the base is like, hey, I want to be 1, and the exponent is like, hey, well, look, that's what I do, right? I turn things into 1. So there's no conflict here. This would just go to 1. Here's another one, 0 to the infinity. So the base, right, is getting smaller. So you get a really, really small number, and you're raising it to a big power. What happens when you take a small number and raise it to a big power? Think about that. Let's take a small number. I know 1/2 isn't that small, but that's smaller than 1. And let's raise that to a big power. Not so big. Let's go to the 3rd power. So you have a small number raised to a big number. This would become 1/2 times 1/2 times 1/2. That's 1/8. That's smaller than what it started as, right? It started as 1/2, cubed it. Now it's 1/8. It's smaller. So again, the base is like, hey, I want to be small. And the exponents are like, hey, I'm going to keep multiplying you times yourself, and you're going to get smaller and smaller and smaller. So this is just going to head to 0. So we have to understand, when is it that we have an indeterminate form where we don't know the answer, and when is it that we don't have that, and we can just say what the answer is. So the key indeterminate forms that we have here are these. And remember, these are on that limit summary sheet right here. 1 to the infinity, 0 to the 0, infinity to the 0. Those are indeterminate forms, along with these others. But okay, so let's get going. We know how to handle 0 over 0 or infinity over infinity. We can use L'Hopital's rule. But what if we have something different? So here's our first example. So x is going to infinity. Let's talk about what happens here. This is headed to infinity, right? And then look at what's happening inside of here. You're getting something that's like 1 over infinity. Where does that go? When you have a fixed number on top, right? 1, and then the bottom gets big, where does that go to?
0.
0, right? That goes to 0. So this bottom is, that's that bottom. That is really going to sine of 0. But what is sine of 0?
0.
0. So that is 0. So what we have is something like this, infinity times 0. Now, this is an indeterminate form because one thing is getting big, the other thing is getting small, right? We're not saying it is 0, it's approaching 0. We're not saying x is infinity, we're saying it's approaching infinity. So big number times small number, don't know. Okay? Don't know. Can't use L'Hopital's rule, right? Can't use L'Hopital's rule because it doesn't look like 0 over 0 or infinity over infinity, right? So how do we handle this scenario? There is a standard kind of trick that we do every single time we ever see infinity times 0 or 0 times infinity. All right, you ready for it? What you're going to do is you're going to pick one of the two things, right? There's two things here. There's the x and there's the sine of 1 over x. You're going to pick one of them. And what you're going to do is you're going to drop it into the denominator. What? What the hell do I mean by that? Okay, watch. I'm going to choose to pick the x, all right? I'm going to leave the sine of 1 over x up here. And I'm going to choose to take this x and drop it below the sine of 1 over x. But when I drop it, here's what I really need. I'm going to put 1 over x on the bottom. Look at that and just agree with me that that's the same as the original problem. Because if I were to do, this is like sine of 1 over x over a fraction, I could flip the x back up and the x would really be just right next to the sine. So it's just me rewriting it in a different way. It's the same exact expression, right? But take the limit now and look at what you have. So we already know where this goes, right? Didn't we already say that if x goes to infinity, that's going to go to 0, right? And then over, and now look at 1 over x. Where does 1 over x go?
0.
0. And now don't we have 0 over 0 now instead of infinity times 0? See, that's just clever. That's just a little clever trick we're going to do. Anytime we see infinity times 0, we're going to pick one of the two and drop it to the bottom. Now, you might be asking, why didn't we leave the x and drop the sign? I'll show you why I didn't do that after I finish this. Okay, so now that we've got this, we can use L'Hopital. So I want to do the limit as x goes to infinity. Okay, careful. You have to take derivative of the top. And when I say the top, I mean everything up there. So when you take derivative of that, that's chain rule, right? You first start out derivative of sine of something, which would be cosine of 1 over x, times, now you have to take the derivative of 1 over x, right? You have to take derivative of the inside. And remember, that's really just x to the -1, right? We're taking derivative of that, which would be -1 x to the -2, which is really just -1 over x squared. I'm just using power rule there. So I can slap that over here, -1 over x squared. Any questions on where I got that? Okay, I'm done with the derivative on top. Now I take the derivative of the bottom, which is the green. So I take derivative of 1 over x. Again, right? Didn't I just take derivative of 1 over x just a second ago? So I already know what that answer is going to be. That answer is going to be -1 over x squared again. And do y'all see what happens? Those cancel, right? Don't they? And so what you're left with is the limit as x goes to infinity. The only thing left here is cosine of 1 over x. And now let x go to infinity. We know that 1 over infinity will go to 0. So that means this thing is headed to cosine of 0. But cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1. So it's kind of weird, but what we had to start with was something that was getting really big times something that was getting really small. We didn't know who wins. It turns out neither of them win. This doesn't get really big and it doesn't get really small. It's like they compromise, they shake hands, they say, we're just going to meet at 1. And that's what happens. So the trick, infinity times 0 or 0 times infinity, you take 1, drop it. Why didn't I drop the other one? Let's see why. So what if I would have started with this? I said to myself, oh, okay, yeah, that's infinity times 0. Okay, I've got to drop 1. So what if I leave the x there, leave the x on top, and drop this one? I would have to do 1 over sine of 1 over x. Do you all agree that's the same thing? I mean, it is, right? You could bring that sine of 1 over x back up. But why do you think I didn't do it this way? What seems harder here?
It's because of that x on the denominator.
Yeah, we're going to have this when we do L'Hopital. The derivative of the yellow is easy, right? The derivative of the LO is just going to be 1. But you have to take derivative of the denominator as well. And the only way to take derivative of the denominator is if you use the quotient rule. Because it's 1 over that function of x. So you've got to do a quotient there. You can't, well, you could rewrite it. You could, if you want, rewrite that whole thing as sine of 1 over x all raised to the -1 and then use your chain rule. But either way, I'm going to need chain rule or quotient rule to take that derivative, and I don't feel like doing that. Whereas when I did it the other way, right? When I did it like this, thinking through it, I said, okay, if I drop the x, I get a 1 over x. I don't mind taking the derivative of 1 over x because that I can just rewrite and do power rule. See, I didn't have to do a quotient rule here because this is really x to the -1, which is easy to take the derivative of. Whereas here, 1 over sine x, I can't do that simple power rule. This is actually some chain. Do y'all follow that? I'm not saying that this won't work. I'm just saying I don't want to do it this way because this is harder. So I'm going to stop here. Don't feel like that. Let's do another one. Okay, here we go. The limit as x goes to infinity of x times e to the -x. So I've got to know what's happening first, right? You can't do anything unless you know what's happening. So I hope it's obvious that this goes to infinity, right? X is going to infinity. And now I need to know what e to the -x goes to. So doesn't that go to e to the -infinity? Isn't that really kind of what's happening there? You're replacing the x with infinity. So it's e to the -infinity, which means that if I look at the graph of e to the x, here's e to the x. I want to know what's happening at -infinity. So what happens is I move out here towards -infinity, right? This way. Where is my graph headed? To what?
0.
0, right? Do you see it's asymptotically approaching 0? So that means that this thing is headed to 0, and so I have infinity times 0. That make sense? Anytime I see infinity times 0, I'm going to drop 1. Which one would you like to drop?
The
X.
x.
Yes.
The x. Okay, so if I drop the x, it'll become a 1 over x on the bottom, right? Let's actually look at the two options we have. Okay, here are my options. I can go this route or I can go this route. All right, one thing I could do is I could drop the x down, leave the e to the -x on top, and put a 1 over x on the bottom. That's first option. The other option would be to leave the x on top and move the e to the -x down. So what would it become on the bottom?
e to the x.
Just e to the x. Right? Isn't that, if you have a negative exponent, can't you drop it down? So isn't putting e to the positive x on the bottom the same as having an e to the -x on the top? Which one of those two would you rather do the derivative of the top and bottom of? The left or the right?
The right.
The right. Because these derivatives are easy. Derivative of x is 1. Derivative of e to the x is itself, e to the x. Where over here, I'm going to take derivative of e to the -x, which is pretty easy, but there's some chain rule involved here. And then I take derivative of 1 over x, which we did a second ago, is -1 over x squared. I think this is probably better. Don't feel like dealing with that. I'm going to do this way. So I bring in L'Hopital. Derivative of top is 1. Derivative of bottom is e to the x. So now if I try this limit, this on top is fixed, right? It's not doing anything. And e to the infinity, right? That's where this is headed. E to the positive infinity, which if we go back to that graph, now we're on the e function, but we're headed out to positive infinity, which means that this graph is taking off to positive infinity as well. So the denominator is getting infinitely big. And anytime you have a fixed number over infinity, it goes where?
0.
0. So what happened here? We started with the limit. The first piece x was getting infinitely big, and e to the negative x was getting really, really small. They were kind of battling each other. In this problem, the e to the negative x wins, okay? It's like, yes, the x is getting big, but the e to the negative x is getting small so fast that it overpowers the x. Not like the one we did before, right? The one we did before, they compromised, right? They said, you know what? Neither one of us win. Shake hands. Answer's 1. Okay. Why don't I let you look at that for a minute? Take a minute to see how you would approach this. See what's happening first. You do need to know what the natural log function looks like because we're approaching 0 from the right. So see if you can at least figure out what these are going to, and then proceed from there. I'll give you just 2 or 3 minutes just to kind of look at it. If you have a question, let me know. Y'all ready? So where is sine of x headed? As x goes to 0, sine of 0?
0.
0, right? And then what about the natural log of x? You've got to know what the graph looks like, right? This is natural log of x. And we are approaching 0 from the right. So we're approaching 0, right, from the right-hand side, and the graph is diving down to negative infinity. So this is times negative infinity, which again is an indeterminate form. It doesn't matter that it's negative infinity. You have a small number times a very big negative number. Who wins, right? So we've got to drop 1, right? We need to drop 1. Do I want to look at the 2 options again? Was that helpful to see them both? and just kind of eliminate the one you don't want to do?
Yes, please.
Okay, let me do that. So let's see here. My two options would be I could drop the sign, so it look like this, natural log of x over 1 over sine x. And then the other one would be limit x goes to 0 from the right. I can leave the sign on top and then do 1 over the natural log of x, like that. Now, notice on both, does anyone have any questions on this whole idea of like dropping one down? Y'all understand how this is working algebraically? So notice on both of them, just look at the tops, the natural log of x. I don't mind taking derivative of that. Derivative natural log of x is 1 over x. So that's not a problem. Over here, the top is sine x. Derivative of sine x is cosine x. So I don't have any issue with either the left or the right in terms of taking the derivative of the top. The bottom, on the other hand, is different because I have 1 over sine x. I have to take derivative of that, right? Which means I would have to do a quotient rule here potentially. And then same with 1 over natural log of x, I would have to do a quotient rule here. But 1 over sine x from pre-cal is actually cosecant x, isn't it? Like this could be rewritten natural log x over cosecant x, like that. And the reason I like that is because back when I took Cal 1 this semester, right, when we were going over formulas, I asked you to, as soon as possible, memorize derivative of sine, cosine, tangent, and to know that there are derivatives for the other trig functions as well. Cosecant of x, the derivative of that is negative cosecant of x, cotangent of x. So I do have the derivative of that if I need it right here, right? So if I come back here, I'm going to keep working with the left one. If I apply L'Hopital's rule, I get limit x approaches 0 from the right. The derivative of the top is 1 over x, because that's a derivative of natural log. And the derivative of the bottom is negative cosecant x cotangent x. It's not pretty, okay? It's not pretty, but let's keep going, all right? Let's keep going. Any questions up to this point? All right, all of this is really giving me a headache. So what I'm going to do now to make my life hopefully a little easier is I'm going to rewrite this as negative 1 over sine x times cotangent. What's cotangent? Isn't that cosine over sine? Because tangent is sine over cosine. So cotangent should be cosine x over sine x. All I'm doing is just trying to make this a little easier to look at. This is equal to limit x approaches 0 from the right of 1 over x over negative cosine of x over sine squared of x. Boy, this looks like it's getting bad, huh? All I did there was put these two fractions together, multiplied across. Now, the reason I did that is because now I have a fraction over a fraction, so I can reciprocate the bottom fraction up. I'm wondering if this was the better choice now. Let's see. I wanted to keep going here. It's going to be 1 over x, that's on the top, but now I bring the sine squared x up over negative cosine of x. So I just brought the bottom fraction up and flipped it, which is limit x approaches 0 of sine squared x over negative x cosine x. Whew. All right, let's check to see if we did anything good here. Let's let x go to 0. What is sine of 0? 0, right? Squared 0. So my numerator is headed to 0 right now. And then on the bottom, if I plug in 0 here, I get negative 0 times cosine of 0. Cosine of 0 is 1. So in the bottom, I'm still getting 0, aren't I? I have 0 over 0. Shit. That didn't help, did it? I mean, but we could do what?
Do it again.
We could do L'Hopital again because we have 0 over 0. Oh my. Maybe we should have done this one. I'm just having you think that way right now, but I'm going to finish this off. I'm going to see if it'll go. Come on. Let's not give up. We've come too far. Let's take the L'Hopital on this. So when I do L'Hopital here, I've got to do derivative of the top over the derivative of the bottom, right? On the top, let me take the derivative. I hope you follow this. That's the derivative of the top. Why? Because that's really sine x squared. So when we take the derivative, the 2 comes out, 2 times sine x to the first power, then times the derivative of sine, which is cosine. All over the derivative of the bottom, but the bottom is a product. So I've got to take the derivative of the first one times the second plus the derivative of the second times the first. Geez. Derivative of the first one is -1 times the second one. Plus, let's see, the derivative of the second one is negative sine x times the first one. Oh my gosh, is this terrible or what? Any questions where I am right at this point or no? We're here. We made it. Okay, let's see why we have an answer now. Let's let x go to 0. We have here 2. Sine of 0 is 0. Okay, times cosine of 0 is 1. So the numerator is headed to 0. 2 times 0 times 1. The denominator, I'm really hoping this is not headed to 0, because then we'd be 0 over 0 again. I would start to lose faith that I'm never going to get this. But look at this right here. If x goes to 0, cosine of 0 is 1, and -1 times 1 is -1. So I have -1 there. And then I have plus, and now look at these two together. Sine of 0 is 0 times x is 0, 0. Isn't that just 0 there? But -1 plus 0 is -1. So you're getting 0 over -1. Is that bad? Is that indeterminate? No, that's 0. And that's our answer. So I told you all last class, like L'Hopital is awesome, but it's not like the miracle pill, okay? It doesn't fix everything for us. It makes limits easier a lot of times, but sometimes you still got to work. Questions? Shall we try it the other way? Maybe it was better, maybe not. I don't think it's going to be. Let's see. Okay, let's do this one. All right, so if I do L'Hopital here, try and give myself some room. If I do L'Hopital, the derivative of the top is cosine x, so I'm like all happy about that. But when I do the bottom, I have to treat that like a quotient. Let's do that over here on the side. 1 over natural log x. Let's do the derivative. So you start with the derivative of the top, right? I'm running quotient rule here. Derivative of the top is 0 times the bottom minus the derivative of the bottom. Derivative of the bottom is 1 over x times the top, which is 1. And then all over the bottom function squared. 0 times natural log x goes away. This just gives me a -1 over x over natural log of x, but then squared. So that's the derivative of the bottom. Negative 1 over x over natural log of x, but that's squared. And I believe right now, if we plug in 0, we're in trouble. Let's see why we're in trouble still. If I plug in 0, what does this go to right there? What's negative 1 over 0? Fixed on top, denominator gets small. That should blow up, right? That should become infinite. Positive or negative, I don't even care. It's just getting infinitely big. And then look at this one right here. If I try and plug 0 in here, natural log of 0, well, we did that graph a second ago, right? When we approach 0, it goes to negative infinity. So this goes to negative infinity, and then square it. It's still infinite. And do you see we still have infinity over infinity there? Which means I need L'Hopital again. But I don't feel like doing L'Hopital again because this derivative is going to suck even worse. Like it's going to get real bad, real fast. Because I got to take derivative of negative 1 over x. I got to take derivative of natural log of x squared. So I'm going to have chain rule. This was better. This was better because I was able to turn this into a bunch of sines and cosines. Wow, that problem didn't look like it was that bad. That's actually in your homework set. So that's number 26 out of the book. How y'all feeling? I'm getting the looks on your faces. I'm not quite sure if this is what I'm seeing. Y'all seemed real excited about L'Hopital last class. Maybe not so much anymore. All right. You ready for something new? Okay, I have this one. Limit x approaches 0 from the right of 1 over x minus 1 over sine x. All right, we need to be extremely careful here. X is approaching 0 from the right, right? I mean, sorry, yeah, x is approaching 0 from the right. So let's take a look at this first one, 1 over x. Where's that headed? Well, the top is fixed, right? The number 1 is a fixed number and it's positive. And the bottom is headed to 0, but we're coming in from the right. From the right of 0, those are going to be positive numbers, right? So I've got numbers that are getting really small, but they're positive. So what happens when we have fixed positive over 0 positive?
Positive infinity?
Positive infinity, right? That's headed to positive infinity. So we've got infinity there. That's what 1 over x is doing is x approaches 0 from the right, 1 over x goes to positive infinity. Now, let's look at the other one. The other one, you have fixed on top, the number 1, and it's positive over. Now, what is sine of 0?
0.
0, right? So it's headed to 0 here, but you have to think about what's happening on the sine function as you approach 0 from the right. Right? If I'm on the sine function, I'm approaching 0 from the right. These values on the sine function are positive. They're above the x-axis. So that tells me that these, yes, the denominator is going to 0, but they're always positive. So that means that I, again, get positive infinity there. So this is turning into infinity minus infinity. And infinity minus infinity is an indeterminate form. I have a huge number minus a huge number. I don't know who wins. Which one's bigger? Don't know. So I have to determine this. This is an indeterminate form. Questions? Come on, y'all look like you're stunned or something. Are you okay?
What would we write if it's an indeterminate form?
You don't need to write anything. You just need to continue to work the problem out.
Okay.
If this would have been infinity plus infinity, you're done. Like the answer is infinity. Because if I take a huge number and add another huge number, that they're both positive, then it's a huge number. But when I subtract two huge numbers, I can't tell you what happens. So what we need to do now is something. Shoot, I don't know. Let me see here. Infinity minus infinity. What in the world can we do with this? This is not like the problems I've shown you, right? The problems I've shown you before this one were 0 times infinity, right? That's what we were dealing with. And I said, take one and drop one. We don't have this here. We have infinity minus infinity. And I have not really told you what to do here. Anybody have like a gut instinct of what I could do just algebraically to that expression?
We can turn it into sine x minus x over x times sine x.
So what did you do there?
Oh, getting the common denominator, I
Yeah,
guess.
you can just put these two fractions together, right? And get a common denominator. I mean, why not? Shit, we may as well try it, right? If we get one fraction, then maybe we'll get lucky and we'll get 0 over 0 or infinity or infinity. So let's get a common denominator. I have to multiply this by sine x over sine x. I'll do a different color. So I'm going to multiply this sine x over sine x, and over here multiply x over x. If I do that and put those together, I'll get limit x goes to 0 from the right of, let's see, my numerator on my first fraction is sine x, and then I can subtract the numerator on the second fraction, which is x, and put that all over the new common denominator, which is x times sine x. That seems like a fair algebraic move. Let's just check now to see what we get when we let x go to 0. So if x goes to 0, that's 0. Take away, well, that's 0. 0 minus 0 is 0. So the top's headed to 0. Looking good so far for L'Hopital. And then on the bottom, we get 0 times, well, sine of 0 is 0. So 0 times 0 is 0. And so the bottom's headed to 0 as well. And I'm happy, right? I can at least try L'Hopital. So this is equal to, by L'Hopital's rule, the limit as x goes to 0 from the right. Okay, derivative of the top and bottom separately, right? Derivative of the top is cosine x minus 1. Derivative of the bottom is a product rule. Right? That's x times sine x. So you have to do a product rule. 1 times sine x plus the derivative of sine x is cosine x times the first function. So there's my product rule on the bottom. What now?
We can put in 0 and see if it.
Yeah, let's see. Let's see what happens. Let's hope for the best here. What is cosine of 0?
1.
1 minus 1. Shit, the top's headed to 0. All right, well, that's not necessarily bad unless the bottom's headed to 0 as well. All right, here sine of 0 is 0. That's 0 plus, shit. These two together is 1 times 0, which is 0. So I've got 0 over 0, which means
We do it again.
I'm going to try it again. I'm going to try to do L'Hopital again. Come on, L'Hopital. Come on. All right. Derivative of the top. Derivative of cosine of x is
Negative
negative
cosine.
sine. Yeah. Minus derivative of 1 is 0. So that's all I have on top. Okay. Bottom is going to suck. Just be careful. This is really just sine x, right? So the derivative of that is just cosine x. Plus, now when I take the derivative of this in blue, that's a product rule, right? That's a product rule. So I'll do it kind of carefully here. I've got to take derivative of cosine, which is negative sine of x, times x plus now the derivative of x, which is 1 times the cosine of x. Need to extend my bar there. That looks bad, but it's going to work this time. It's going to work. Watch. Let's let x go to 0. That's negative sine of 0. That's just 0, right? So the top's headed to 0. So at that point, you're like, shit, you're like getting frustrated, right? Like, oh my gosh, here we go again. But cosine of 0 is 1 plus, now look at all this. Sine of 0 is 0 times 0, that's 0. And then plus, look, cosine of 0 is 1 again, right? And so what's the bottom? 2, right? That's not 0 over 0. That's 0 divided by 2, and 0 divided by 2 is 0. Yay. Let's take a look again at that. We had this. We said, okay, we had to be real careful. Fixed positive over 0 positive infinity minus fixed positive over 0 positive infinity again. Infinity minus infinity, don't know. Shoot, what do? This is not the case where you drop one. So common denominator, right? Robert suggested common denominator, put it together. It worked, right? We put them together, got 0 over 0, ran L'Hopital once, still got 0 over 0, ran L'Hopital again, and we got 0 over 2, which is 0. So our answer is 0, and we are happy. Okay. Let me see here. I want to bring something up. Let me see if I can't find this. Let's see how quickly I can find this. No. Nope, give me a moment.
Wait, is it supposed to be 2413 or 2414?
It's 2414. This is Cal 2. I know I just gave them this review. Hold on. There we go. I think that's it. This is a Cal 2 exam. Okay. This is the second exam I gave 2 years ago. Here's the exam. Okay. And I'm just going to work through, I'm just going to take you down. Hopefully it's in here. Crap, man. It's not in that one. One more place. Yeah, okay, I'm gonna have to look somewhere else to find it. There's a problem in the Cal 2 where, like, at the very end of the problem, we have to do L'Hopital. And I'll look for it. If we take another break where I give you an opportunity to work on a problem, I'll go look for it. I was gonna have us work that problem, not the whole problem, just that little piece of the bigger problem to show you, like, this stuff just pops up in different places. Like, you're doing a some other problem, and all of a sudden you need L'Hopital because you get 0 times infinity. So you got to figure out what happens. It's like I don't want to give up. Y'all can just take a breath for a second. I know it's here. Exam 2 review. There we go. Here we go. Right here. We had to do this right here. T natural log T. And we wanted to know what was happening as T went to 0. Don't worry about the rest of the problem. Just right there, I want to know what T natural log T does when T goes to 0. So let's try that ourselves. We haven't done that, right? No, we haven't. So what if I gave you this problem? Limit, I'm going to use T instead of X. T goes to 0. I need to say from the right. It was implied in the Cal 2 problem. So T natural log T. All right, so let's talk about what's happening here. This is headed where? T is headed to
0.
0.
0.
0, okay. Times, okay, natural log of 0. We're approaching 0 from the right. So what does the natural log function do as you approach 0 from the right?
Negative infinity.
Negative infinity.
Yep. So now you get to pick one and drop one. Take a minute. See if you can finish this one off. Take a couple of minutes, 2 minutes. Let me know when you're done. Yes, on the, just answer the poll. When you're finished with this one, say yes. You have to pick which one to drop, right? One of them is far easier than the other. If you're unsure, drop the T. Leave the natural log on top. Drop the T as a 1 over T. So far I only have 5 people that are done. All right. Time is of the essence. I'm going to stop here. This is back to the question from the Cal 2. So we had to figure out what this was. I did the work over here. So I took the t, I dropped it down as 1 over t. And then I did L'Hopital. Derivative of natural log of t is 1 over t. And the derivative of 1 over t is negative 1 over t squared. What did I do from this step to here? Let me take that. What did I do?
You bring the -1, like you flip it and you cancel the t.
That's right. I flipped it. So I brought this up. I brought it up as a t squared over -1 and got rid of it here. And then what happened is one of the t's went away and I was just left with t over -1, which is the same as negative t. And now I let t go to 0 and that just gives me -0, which is 0. So the answer is 0. So like in a Cal 2 class, I'll have students that do this and they'll tell me that this is 0 and that this is 0, but they don't do any of this work. And I take points off, even though it's correct. They put 0 here, but they just got lucky. Like t natural log t goes to 0 is not obvious. You have to show it. All right. So again, just kind of showing you that there are problems that come up later, other classes where you need this. Okay, everybody all right? What we've dealt with so far, right? What we've dealt with so far today, right, is just today, we've said, okay, yes, we can handle 0 over 0, infinity over infinity with L'Hopital. 0 times infinity, we can drop 1, right? Drop one of them. Infinity minus infinity, that's one that we did where Robert said, let's put them together with a common denominator. That seemed to work, okay? We have conveniently avoided anything like this up to this point because those are the most, not confusing, but the most involved. All right, so I'm ready to get into those now. Here we go. So what about something like this? The limit as x goes to 0 from the right of x raised to the x. Well, first of all, we just plug in 0, right? And we say, okay, well, this is going to 0 raised to the 0, right? And this is bad. This is an indeterminate form, right? The base wants to be 0, but a 0 exponent wants to turn it into 1, right? So this we don't know. It's indeterminate. So what do, right? You can't treat it like the 0 times infinity because we don't have 0 times infinity. So you can't drop 1. You can't treat it like 0 over 0 or infinity over infinity and just do your L'Hopital because that's not what we have, right? So how do we deal with this when we have the 0 to the 0? Here it is. You ready? This is going to be weird. What we're going to do is we're going to call this limit y. Okay, I'm going to call the limit y. I'm going to assign that limit, whatever it is, the value of y. So we want to know what y is, right, everyone? I'd love to know what y is. Okay, now why did I do that? I did that because now what I'm going to do is I'm going to bring the natural log in on both sides of this. And you might be asking, well, why in the world are you going to bring the natural log in? Well, the reason I'm bringing that natural log in is because that very powerful property of the natural log that we learned in college algebra, which was this: if you have natural log of x to the n, there's a property that allows you to pop the n out front, and natural log x, right? Natural log is a great way to get things out of exponents, to pull exponents down. And since this is x to the x, I want to pull that x down, but I can only pull it down if I have a natural log. So I make an equation out of this, and then I do the natural log on both sides of the equation. The next step is to pass the natural log through the limit, which you are allowed to do. This is a limit law that way back when we learned limit laws, I just subtly, like very, very subtly went through this. You just have to take it on faith that if you have the natural log of the limit, you can do the limit of the natural log. In other words, the natural log can move inside the limit like that. So I'm just going to move the natural log here and put it on the x to the x. What is that going to allow me to do? Take that x and pop it out here. So my next line is natural log y equals limit x goes to 0 from the right of x times natural log x. Any questions there? Wait a minute. X goes to 0 from the right, x natural, does this look familiar? Wait a minute. We just did that, didn't we? We just did this problem, except we used t. It was 0 times negative infinity. Let's just kind of think through that again. If x goes to 0, this here goes to 0. And then this goes to negative infinity, because that's what natural log does when you head towards 0 from the right. So I'd have to pick one and drop it, right? I'd pick the x, I'd drop it, I'd do my L'Hopital, ... I'm not going to show this because we just did this problem, right? See previous problem. This we know goes to 0, right? That is not my answer. That's what natural log of y is, right? The natural log of y equals 0 is what I've said. Remember, we want to know what y is, right? We want to know what y is. We know what natural log of y is. So now what I do is I use, again, what I learned in college algebra, and that is I have a way of killing off the natural log. To kill the natural log, I have to come in with the exponential function. So now what I do is I take e on the left side and e on the right side. So I do e raised to the natural log of y equals e raised to the 0. And on the left side, the whole reason I brought e in was because the e and the natural log kill each other off. That leaves you with y. And what's e to the 0? What's any number to the 0? 1. So your answer is 1. Right? That's what y is. Y is 1. And y was equal to the limit. That's what we were looking for. Okay. Let's just take a step back. If we have 0 times infinity, we drop 1 down. Infinity, 0 over 0, infinity over infinity, we're ready for L'Hopital, right? If we have infinity minus infinity, I don't know, maybe we get common denominator, do some sort of factoring, do something, right? Those are all handled a certain way. None of those require any sort of natural log. But if you have 0 to the 0 or any of those other indeterminate forms, 0 to the 0, 1 to the infinity, infinity to 0, those three will require a natural log. You will have to come in, set y equal to the limit, natural log both sides, pop the exponent thing down, take a look at that limit. When you take a look at that new limit right here, when you pop this thing out front right here, when you pop that thing out front, I promise you that whatever you have here is going to be a 0 times infinity. It's going to be. And then you just pick one, drop it, and go. All right, let's do another one. All right. How about we do, are we ready for that one yet? Let's do this one. Limit x goes to 0 from the right, tangent x Yeah. To the x. What's tangent of 0? Well, tangent is sine over cosine, right? That's what it is, sine over cosine. So what would happen if I plug 0 in there?
Just 0.
0, right? So tangent of 0 is 0. So I'm going to get here 0 raised to the 0. That's not good, right? I don't know what that is. So 0 to the 0, I go, I need the log, right? So I'm going to call this thing y. And now I'm going to do the log. The natural log on the left. Notice on the right, I'm going to go ahead and insert the natural log after the limit because I know I'm allowed to do that. Okay. Make sure you make a note here. You call this thing y. Set equal to y, right? That way you have an equation to work with. And then you do the natural log on both sides. Take the x, pop it in front. Natural log y equals limit x goes to 0 from the right of x times natural log of tangent of x. What did I just promise you this would become after you pull this out? What did I promise this would become?
0 times infinity.
0 times infinity, or it could be infinity times 0. I promise you it's going to now be the situation where you need to drop one. Okay. I'm going to drop the x. I really don't want to drop the natural log tangent x. I do not want to drop that down because that would suck to take the derivative. So what I'm going to do now, this is still just algebra. Okay. I've not done L'Hopital. I'm going to leave the natural log of tangent x on top. And on the bottom, I'm going to do 1 over x. Oh my, this looks horrible. Hey, we never checked to see that this was 0 times infinity. I promised you it would be, right? Can we check it real quick that it is? That goes to 0 times, what is tangent of 0? Tangent of 0, right? But then we still have natural log of that. And the natural log of 0, well, we're approaching 0 from the right. We just said a minute ago, a couple of times, that goes to negative infinity, right? The natural log function dives down. So we do, in fact, have 0 times negative infinity, which I told you it would be. You don't necessarily need to check that, but if it just gives you peace of mind to know that we do need to drop one, there, I'm hopefully convinced you. Okay, well, L'Hopital time. Derivative of the top. Derivative of that. Well, derivative of natural log of anything is 1 over that, right? So I need to put 1 over tangent. Times, now I need to take derivative of tangent, which is secant squared x. And then this whole thing divided by the derivative of the 1 over x, which we've done now several times today, negative 1 over x squared. Ooh. All right. I'm gonna go over here on the side. This looks like a mess. 1 over tangent. So what I'm doing is I'm gonna come back to this, all right? I'm gonna come back to this. I'm just going to clean it up though. I'm going to see algebraically if I can make that look better. So 1 over tangent is the same as cotangent, right? So this thing is cotangent x. And cotangent is cosine over sine. So that's really cosine x over sine x times, now what about secant? Secant is 1 over cosine, right? 1 over cosine, but then squared. So this looks like 1 over cosine squared x. But that whole thing is on top of negative 1 over x squared. One of these cosines cancels. And I'm going to bring the x squared over negative 1 up and flip it. So what's my new numerator? What does the new numerator look like? What's the only thing I really have left on top?
X squared.
X squared,
Uh,
right? It's
yeah.
those together.
And then it's over, I guess, negative sine cosine.
Yep, negative sine x cosine x. That's not so bad, right? I mean, that's not terrible. It sure as hell looks better than this, doesn't it? Okay. I mean, welcome to calculus. I mean, this is just the way it is. Okay, x squared over negative sine x cosine x, cleaned up. All right, let me check what happens now. If x goes to 0, what's wrong, dude? If x goes to 0, you get 0 on top, and then sine of 0 is 0, cosine of 0 is 1, so unfortunately we get 0 on the bottom. Looks like we're going to need L'Hopital again. All right, natural log y equals, by L'Hopital's rule, limit x approaches 0 from the right. Derivative of the top is 2x. Derivative of the bottom is crap. Hey, are y'all okay with this? I don't like that negative down here. I just personally don't like it. Is it all right if I move that negative up here and just get rid of it down here? Is that all right with y'all?
Yeah.
And then when I took that derivative, it's now negative 2x. You can do that with negatives on fractions. You can have it on the top or the bottom or out front. So when I take derivative of the bottom, I've got a product rule. So derivative of sine is cosine times cosine again, plus the derivative of cosine, which is negative sine x, times the first one, sine x. Oh, I'm excited. Do y'all see why I'm excited? When x goes to 0, the top, where's the top going? 0, right?
0.
But look at the bottom. Do you see this right here? That's going to be 1 times 1, right? So that's going to be 1 plus, and then these two together, that's going to be 0 times 0. That's 0. So 1 plus 0, 0. I don't have 0 on the bottom. I have 1 on the bottom. So this is just 0, 0 over 1. So that means I'm there. Natural log of y equals 0. We need to get y. Not natural log of y, we need y, right? So I bring in e now. E to the natural log y equals e to the 0. And that means y is equal to 1. Isn't that the same answer we got on the previous problem? So maybe the answer is always 1. No, it's not. All right. Y'all hanging in there? All right. We're going to do now our final problem. I think this might be the final problem. This is actually a very, very interesting limit, as you'll see when we get to the final answer. What is the limit as x goes to infinity of 1 plus 1 over x raised to the x? I'd like to put a star on this one, maybe a couple, not because this is necessarily something I would give you on a test, although I could, especially if I've done it in my notes. But this is a classic problem, right? This is a classic problem. It's like everyone needs to see this, all right? Every Cal 1 student needs to see this. So let's just check what's happening. As x, be careful, x is going to infinity here, all right? 1 over infinity goes to what?
0.
Fixed over infinity, that goes to 0, right? So you've got something that's headed towards 0, right? But you're adding 1 to it. So the base is headed to 1, isn't it? But where's the exponent headed?
Infinity.
Infinity. 1 to the infinity is an indeterminate form. The base is like, I want to be 1. And the exponent's like, no, I want to make you bigger and bigger and bigger, right? This is indeterminate. So we need to do something here, right? 1 to the infinity, you're going to bring in a log, right? That's what I've told you. For those 3 forms, 0 to the 0, 1 to the infinity, and infinity to the 0. Those 3 types, you're going to bring in the log. So let's call this thing y. And let's go ahead and do the natural log on both sides now. So natural log of y equals limit. X goes to infinity. I'm passing the log through the limit. And now I've got 1 plus 1 over x to the x. Okay, so set it equal to y, natural log both sides, pass the natural log through the limit, and now you're ready to pull and pop that thing out front. It's the same kind of format, right, for all these problems. So we get natural log of y equals limit, x goes to infinity, but now that x popped out in front, and then I have natural log of 1 plus 1 over x. Guaranteed that's going to be infinity times 0 or 0 times infinity. Do you want me to check it or no? No? Okay. It's actually infinity times 0. You can, yeah, I won't check it. It's infinity times 0. So now I need to drop one. I'm going to drop the x. And I'm going to drop the x because, well, again, I don't want to drop the natural log because that thing on the bottom would be 1 over this natural log, and I sure as heck don't want to take the derivative of that. So I'm just going to go with that. Dropping that x down as a 1 over x. L'Hopital, here you go. Okay. The derivative of the top over the derivative of the bottom. Hey, I'll do the derivative of the bottom first because it's easy, right? Easy because we've done it like 4 times today, 5 times. What about the derivative of the top one though? So derivative of natural log of anything is 1 over that anything, whatever was there, right? So it's 1 divided by whatever was inside. Times, careful, what is the derivative of what's in here? So you can do them separately because there's addition, right? So you get derivative of 1, which is 0, plus what's derivative of 1 over x?
Negative 1 over x squared.
Negative 1 over x squared, right? Again, it's like the 5th or 6th time we've had that now. Ooh. Ooh. Those are the same thing. Right? Those are the same exact things. Just cancel them out. So maybe we don't even have a problem. Maybe at this point, we don't have any more 0 over 0, infinity over infinity. I need to check it and see what's left. The only thing that's left is that. Okay, that's the only thing left. And if I let x go to infinity here, the only thing that happens is this piece goes to 0, right? So you're left with 1 on top and 1 on the bottom, 1 plus 0. So 1 over 1 is 1, isn't it? So we get the natural log of y equals 1. And now you want to get y, right? Get rid of the natural log. So you bring e in. E to the natural log of y equals e to the what?
1.
1. Okay. The left side just becomes y, and the right side is just e. E. What? The answer is e. So what we're saying is this. We're saying that if you take the limit as x goes to infinity of 1 plus 1 over x raised to the x, your answer is e. In fact, this is a definition for e. If you'd like to give somebody a definition for e, that is a satisfactory definition. Like right now, if I asked you, hey, if someone asked you, hey, what's pi? You'd say, oh, pi is just the circumference of a circle divided by its diameter. That is a definition for pi. Give me any circle, take its circumference, divide it by the diameter. That's what pi is. Very clean, nice formula for pi. You want to know what e is? E is actually can be defined as a limit. It's this limit right here. Now, I want to make sure that you kind of understand what the heck I'm saying here. So I want you to appreciate this. If I were to graph this as a function, f of x equals, in parentheses, 1 plus 1 over x, okay? All of that raised to the x. Here's the graph of this function, right? Here's the graph. Now, if I graph the horizontal line, y equals e, I want you to notice that the red curve asymptotically approaches the blue, which is what we were saying. We said the limit as x goes to infinity of this function. So if you look at this as a function and you go out to the right, it gets closer and closer and closer and closer to e. And that is what's happening. Here's another way you can do it. Another way you can think about it. Let's take a number for x. Let's pick a number for x. How about x is equal to 1? I'd like for you to plug 1 into this. Let's see what we get. We can do this in our heads. 1 over 1 is 1, right? 1 plus 1 is 2. And 2 to the first power is 2. So if we do that, plug it in, we'll get 2. Yes? Let's take a bigger number. X equals, let's go 10. And plug it in here. So what would happen? I get 1 plus 1 over 10 raised to the 10th. Isn't that what I would get? I'm going to get on my calculator and do that. I'm going to do 1 plus 1 over 10. And then I'm going to raise that to the 10th power. And the number I get here as an answer is 2.59374. Now, what was E? E, if you type E on your calculator and ask your calculator, hey, calculator, what's E? Your calculator is going to say it's approximately 2.71828, right? That's what it's going to say. What this is saying to us is that the bigger and bigger I let X go, the closer and closer it gets to 2.71828. So if I put in here X is 1,000, I'll do that on my calculator. 1 plus 1 over 1,000, raise that to the 1,000th power, I get 2.716. So you see I'm getting better, right? Started out at X is 1, I was 2, then 2.59, then 2.716. The real answer is 2.718. The bigger and bigger X gets, the closer and closer and closer you get to the true value of E. So you can define E to be the limit as you let X become infinite. It asymptotically approaches them. Okay. Questions. I still think there's some stuff I want to talk about. Are there any questions over what I've done here? Y'all seem like y'all are sick. Are y'all okay? Just something weird today.
I actually am sick. I've been sneezing up a storm this whole time, so you're
Maybe
right.
this will make you feel better then. Maybe you just needed the L'Hopital medicine today and you'll start feeling better. All right, we still have 10 minutes. How about I give you one? All right, let's do this. Let's go. Yeah, let's, shall we pull up an old test? Let's pull up an old test. Let's see if I have a L'Hopital with this type on an old test. That's this semester. Hold on. What the heck? How many exams have we taken? 2? There we go. That's right. We'll put the poll up. Let me know when you're done. This is a problem directly off a test from a year ago, I think. We've got 6 of you that say you're done. Okay, half of you are done. If you've finished, here's one that you can kind of mess with for the next 3 minutes if you want. Limit x approaches pi over 2 from the left of tangent x raised to the cosine x. You have to know what tangent does at pi over 2 from the left-hand side. So you might have to look back at a graph if you don't know. Okay, I only have about a minute left. Let's talk about the first problem that I gave. 1 over x to the x. So this is 1 over 0 goes to infinity. And then you raise it to the 0 power. This is something we don't know. We let this equal y. We take the natural log on both sides. We pop the x out. This is guaranteed to be infinity times 0 or 0 times infinity. We drop, in this case, the x down. The derivative is a little tricky. The derivative of the top, derivative of natural log of 1 over x is 1 over 1 over x. 1 over 1 over x. And then the derivative of the inside is negative 1 over x squared. We've seen that now 6 or 7 times. And then again, the derivative of the bottom again is derivative of 1 over x, which is negative 1 over x squared. These cancel. And then before you do anything else, just flip the x up, and this just becomes 1 over x just becomes x. And now take your limit, let x go to 0, and this becomes 0. And then you just do e on both sides. Do I need to clarify that for anyone? Okay, class is over. I'm going to finish the other problem, so you're welcome to stay. Finish your homework for 3.7. I would say do as many problems between numbers 1 and 38 as you possibly can. 1 through 38. And then I
Have a
will,
nice day.
yeah, go ahead if you got to go. I just want to mention on Thursday, my daughter has to have 4 teeth pulled in the morning. I don't know, she's got braces. She's going to get, well, she has braces and they're having to pull teeth. I don't know if any of y'all have ever had that happen to you before. I had never heard of that before, to pull 4 freaking teeth for braces. Seems extreme, but anyway, they're going to pull 4 teeth on Thursday. And so anyway, that's going to happen at 8 o'clock in the morning. So she's going to be here at home with me on Thursday. So I'm just giving you a heads up, like, you know, if I'm in the middle of class and she's like, Daddy, you know, like, well, I don't even know if she'll be able to do that, but I'm going to be keeping my eye on her in the other room. So just an FYI, I might have to cut out for a few minutes or something. Yeah. Okay. And now the other thing is this one here. So on this one, we're approaching pi over 2 from the left. You have to know what tangent looks like. This is what the tangent function looks like. And at pi over 2, you have vertical asymptote. So as you approach pi over 2 from the left, you head to infinity. And then cosine of pi over 2, you just, you know, cosine is the x coordinate at straight up on the unit circle, and that's 0. So you get infinity to the 0. So as soon as you're there, you can start doing the log and stuff. So I'm just going to be real quick with this. Natural log y equals limit x approaches pi over 2 from the left. And then I'm going to do a natural log, and I'm going to pull the cosine out. So I'm going to pull the cosine out now just to save time. And now I drop 1 down. So really, to save time, I'm going to go ahead and drop that cosine down to the bottom as a 1 over cosine. But that is just secant. So I'm really just going to put a secant down here. Did I go too fast, or does that make sense? That's okay. Okay, L'Hopital. So when I do L'Hopital, limit y, or natural log y, L'Hopital, limit x goes to pi over 2 from the left. Okay, derivative top is 1 over tan x times secant squared x. And then over the derivative of secant x, which is secant x tangent x. And some things get nice here, I think. I can kill off one of the secants right away. And then the tangent over 1 can flip up as a 1 over tangent like this. So that gives me yuckiness, I guess. So I've got limit x approaches pi over 2 from the left. Okay, what do I have here? I still have a secant on top, and I have 2 tangents together. So I have a secant x over tangent squared x. I think I'd like to get that in terms of sine and cosine. This is 1 over cosine x over tangent is sine x over cosine x, but I'm squaring it. So it's sine squared x over cosine squared x. And then I can flip again. What a mess. Natural log. I thought this was going to go a little faster than this, sorry. Okay, what's left? One of the cosines cancels. So I just have a cosine on top. And on the bottom, I have sine squared. This is not a problem because cosine of pi over 2 is 0, but sine of pi over 2 is 1. So I just get 1 squared on the bottom. So that's just 1. So you get natural log of y is 0, sorry, and then do e on both sides. E to the 0 is 1. We get 1 a lot, don't we? Okay. We'll see you. I'll be in my office at 4.
Sir,
Yes.
before office hours, I wanted to ask you, could you please upload the videos for March 22nd and March 24th?
22nd and 24th? I didn't upload those?
I don't think so. Last I checked,
Wait a
they're not
minute.
up there. That's when we
22nd.
just got back.
Yeah, I don't know why those wouldn't be there. Let me check something real quick. Spring class notes today. Okay, so the notes are uploaded. So you're saying the videos from 22nd, 24th?
Yes, sir. Even the class notes from the 24th through.
You don't have the class notes for the 24th either?
No, sir. They're not in that folder.
What the heck? I was trying to see if maybe I uploaded them but forgot to. Let's see. Whoa,
Oh, I see. Yeah, yeah. Second.
22nd, 24th. Okay, well, I will have to go see about that. And you said what notes weren't there?
Class notes, yeah, your like these notes for the 24th are not there, March
The
24th.
24th. Okay, they should be there
Thank
soon.
you.
Yeah, and I'll go look at the videos. Oh,
I appreciate it.
I'm sure I can get to them somehow.
Thank you, sir.
Okay, all right, we'll see you.
See you.